Hello children, today we will study about packing efficiency in case of solids. First of all of you must know what is meant by packing efficiency. Packing efficiency, as the name suggests, tells us about the how close the packing is, the extent of close packing. So packing efficiency basically tells us about the extent of close packing. More close the packing of constituent particles is there in the solid, more efficient that solid is, or its packing efficiency is more. How will you define packing efficiency? Packing efficiency basically defined as percentage space occupied, percentage space occupied by the constituent particles. Constituent particles in case of solid can be atom, they can be ion, they can be molecule, right? So packing efficiency may be defined as percentage space occupied by the constituent particles in a unit cell. In a unit cell. So you can write the formula as packing efficiency is equal to volume occupied by constituent particles upon total volume of the unit cell, volume of unit cell into 100. So this will give you packing efficiency in case of solids. More the packing efficiency, it means better is the close packing in a solid. So more packing efficiency means more space occupied by constituent particles, more space occupied by constituent particles, or you can say less free space or vacant space, and more closely packed constituent particles, more closely packed particles. Since in our syllabus we have to study cubic unit cell in detail, so we will now calculate the packing efficiency in case of three types of unit cell, that is the simple cubic unit cell, body centered cubic unit cell, and face centered cubic unit cell. The most simple cubic unit cell, simple cubic unit cell. Now if you remember, I have already told you in my previous videos or lessons, in case of simple cubic unit cell, the constituent particles are present only at the corner of the cube, right? They are present only at the corner of the cube, like this. 1, 2, 3, 4, 5, 6, 7, and 8. But the actual position is not like this. Since it is solid, so the constituent particles will be close to each other. So the actual position, if you see one of its face, then the actual position will be like this. The particles will be touching each other. This is one particle at one corner. This is another particle at another corner. This is one. I have shown only one face of the cube. It would be like this. They will be literally touching each other, right? Now let us assume that radius of constituent particle, and here I am considering it as atom. Say this unit cell consists of atom. So the radius of constituent particle or atom is r. H length of unit cell, H length of unit cell be A centimeter, right? Now, if I want to calculate the packing efficiency, then this is R. This would be the center of the nucleus of this particle. This is also R. So the relationship between A and R is A is equal to 2R. So in simple cubic unit cell, the edge length of the unit cell is equal to twice the radius of the atom. Now, how to calculate the packing efficiency? So packing efficiency is equal to volume occupied by constituent particles in this unit cell. So in this unit cell, we know since atoms are present at the corner, and at each corner only 1/8 portion of the atom will be inside this one unit cell. So 1 by 8 into 8 equal to 1. So in case of simple cubic unit cell, Z equal to 1 atom means only the volume occupied is equal to the volume of one atom. So Z equal to 1 into volume of each atom, volume of one atom, upon the volume of unit cell into 100. Now Z in this case is 1. Since the constituent particle is spherical, so it would be equal to 4 by 3 pi r cube. A is equal to 2r in case of simple cubic unit cell. So in place of A, we can easily write 2r whole cube into 100. So when you solve it, it comes out to be 4 by 3 pi r cube upon 8 r cube into 100. So this will cancel. When you solve it, it comes out to be 52.4%, right? So this is the percentage space occupied in case of simple cubic units. Now if this much space is occupied, it means the free space in case of simple cubic unit cell means vacant space is equal to 100 minus 52.4. So it comes out to be 47.6%. Means in simple cubic unit cell, approximately 52% is occupied and 47% is almost free space. Now the second case is of centered cubic unit cell. Body centered cubic unit cell. Now as the name suggests, body centered cubic unit cell means the constituent particles will be present at the corners of the cube as well as in the body center of the cube, right? So if the atoms would be like this, 1, 2, 3, 4, 5, 6, 7, 8, and one of the atom would be present inside. For the sake of convenience, I am showing it with some different colors. So it would be present inside the body of the cube. Means you can imagine if you are sitting in the room. So exactly in the center of the room, one of the atom is there and rest of the atoms are present at the corner. But again, this is only for the sake of convenience. Actual position is they are closely packed with each other. And Imagine all these atoms, even the atom which I have shown with red color, this is also of similar atom. That is, the radius is same. So again, let R be the radius of atom, the constituent particle, A, edge length of the unit cell, edge length of unit cell, right? Now we have to find out the relationship between these two. Now, if edge length is A, and we want to find out the relationship between A and R, then you know very well, since this middle atom is present inside the body of the cube, so it will lie in the body diagonal, and body diagonal of the cube will be equal to body diagonal would be this one, which is from top this portion to this one. This is the body diagonal, right? And this body diagonal, for this body diagonal, this face diagonal will act as a height, right? This face diagonal will act as height. So this would be 2a, this would be a. So this side comes out to be root 3a, right? So body diagonal is equal to root 3a. Now root 3a, and how many atoms will be lying in one line? So there would be 3 atoms like this. If this is the body diagonal, it would be like this. Like this is the position, and if this is the body diagonal, so it means this is R, this is R, this is R, and this is R. So 4R is equal to root 3. So you can say A is equal to 4R upon. So this is the relationship between A and the radius. Now same packing efficiency is equal to number of atoms contributed. Now here the number of atoms contributed is 8 atoms are present at the corners, so 1 by 8 into 8. And one of the atom is completely present inside the cube, so that will be contributed fully. So it comes out to be 2. So here the volume occupied will become 2 into volume of each atom, 4 by 3 pi r. And volume of unit cell is same, A cube into 100. Now this is 8 by 3 pi r cube, and it becomes 4r upon root 3 cube into 100. So when you solve it, it comes out to be 68%. It means in case of body-centered cubic unit cell, 68% space is occupied. It means how much is free space? So free space would be equal to 100 minus 68, that is 32%. So we have seen that in case of simple cubic unit cell, 52.4% space is occupied, while in case of BCC, 68% of space is occupied by the constituent particles. It means which one is having better packing? Obviously BCC. Now third comes FC. Third is FCC, face centered units. Face centered cubic units. Now in face centered cubic unit cell, what will happen? The atoms would be present at the corner as well as center of each face. So corner 1, 2, 3, 4, 5, 6, 7, 8. Now center of each face. Again I am showing it with different color, but I assume it that they are of exactly same size. Same atoms are there. So one face, that face, this one, then the back one, then this one, and now the front one. So how many faces are there? 6. So 6 atoms will be there. Now what would be the position in case of single phase? So in single phase, the position would be like this. One of the atom will be like this, another atom like this. It means here the atoms will not these two atoms will not touch each other. It would be like this. There would be some gap. Like so you have to consider only this diagonal. Now this diagonal, this is phase diagonal, and you know if this distance is A and this is also A, so this phase diagonal comes out to be root 2. Now if you consider the radius, then here how many radius will lie? The first one, this one, then this is one, from this to this, then another, then another. So it means it is equal to root 2a is equal to 4. So it is very simple to learn. In case of simple cubic, the edge length is equal to 2r. In case of BCC, since body diagonal is there, so this root 2a becomes root 3a is equal to 4r. And in face center, since only face diagonal is there, so root 2a is equal to 4. Now a comes out to be 2 root 2. Right? Now packing efficiency. Packing efficiency. Now number of atoms contributed into volume of each atom into 100. Sorry, into 100 upon volume of unit cell. Now again, how many atoms will be contributed in this case? So Z atoms are present at the corner. So at each corner 1 by 8 into A plus. At face, since one face is in direct contact with only one face of another cube, so half contribution is there, and since 6 faces are there, so when you solve it, it comes out to be 4. So Z equal to 4. It means in case of FCC, the volume occupied by the constituent particle is equal to the volume of 4 atoms. So 4 into 4 by 3 IR cube becomes E cube. Now in place of A, you can write 2 root 2 R whole cube into 100. So that is 100 is also there. When you solve it, it comes out to be 74%. 74% space is occupied. It means how much space is left? Free. So free space is equal to 100 minus 74, that is 26%. So it is very much clear that out of simple cubic, FCC and BCC packing, the FCC packing is most advanced type of packing, the best one, because it has a minimum free space, that is 26%, and maximum space is occupied by the constituent particles. So this is all about packing efficiency. Similar efficiency is also found in case of HCP packing. In HCP or CCP is similar to this. So in both the packing, the percentage space occupied by the constituent particle is 74%. So that's all for today. I hope you have understood the topic. Thank you.